So here we're going to leave calculations behind for a little bit and talk about the relationship between acid strength and molecular structure. So there are a lot of compounds that contain hydrogen, but they are not all acids. Like, why is H2S an acid, but CH4 is not an acid? I mean, you could write it H4C. Would that make it an acid? No, it's still not an acid. Why is HCl a strong acid and HF is a weak acid? So if we're looking at the binary acids, we need to think about the bond between the hydrogen and the other element. It could be fluorine, chlorine, anything. In order for this to act as an acid, the hydrogen must be donated. And so the strength of the acid is going to depend on the strength of this bond and also on the bond polarity. So bond polarity and bond strength affect how acidic a binary acid is. In order to be acidic, the bond has to be polarized such that the hydrogen is the positive end. So we need hydrogen to be the positive end of this polar covalent bond. Because when we lose H, we need to lose it as H plus, not as H minus. So if we look at HLI, here lithium is less electronegative than carbon, than hydrogen. And so this bond polarity is backwards. The hydrogen is the more negative end of the bond, and lithium is more positive. So this will not be acidic. Could it lose a hydrogen? Sure, but it's not going to lose H+. What about an HC bond? So if you took Chem 1A with me, hopefully you remember me saying that the carbon-hydrogen bond is the one bond I want you to remember between two different elements that's nonpolar. Carbon and hydrogen, the difference in electronegativity is like 0.4, which is just right on that line, and the carbon-hydrogen bond is nonpolar. So this is not polarized at all. Here, fluorine is the most electronegative element, and here we have hydrogen. And so this gives us a bond polarity in the right direction. The hydrogen's the positive end. The other thing that matters is bond strength. So if the bond is stronger, it's harder to lose the hydrogen ion. And so we might wonder, well, why is HF not a strong acid? That's a really polar bond, right? It's polarized in the right direction. Why isn't it? Well, because this bond is strong. 565 kilojoules per mole. As we go down the halogens, the bond energy decreases. Why does it do that? Because as we go down a column in the periodic table, a group, the atoms get larger, right? And so bromine is a much larger atom than fluorine. And the length of a bond is related to its strength. So hydrogen can't get very close to big old fat bromine, right? Big jolly ball of, bromine. Big bromine. And so the little hydrogen is going to stick to him, but it's not going to be a close connection. Fluorine is a really small atom. And so the hydrogen can get closer. The nuclei can get closer to each other. Okay? So acid strength is going to increase as we go down. Electronegativity also is going to affect the strength. Electronegativity increases as we go towards HF. So electronegativity increases going up and increases going over. But the effect of size in the vertical direction is more important than the effect of electronegativity. So size is more important, and then electronegativity. So this is one of those things. There will be a question or two on the next exam, the exam over this material, that asks you to put the acids in order of acidity, right? Or asks you to state why this one is not a strong acid or something. So how do you remember that? Well, you can just, memorize it, but that doesn't work very well for me because I tend to forget things more and more. So I've come up with these little things to help me remember. So what kind of an acid is HCl? Strong or weak? Strong. What kind of an acid is HF? Weak. And why do we know that? We memorized the 6 strong acids. That's something you do just kind of have to memorize, right? There's no real shortcut around that. But we know that this is a strong acid and that's a weak acid. So that tells me that the trend going down, weak acid, strong acid, acidity must be getting bigger. Stronger acidity going down. Is H2O an acid? Yeah, but it's really weak, right? Super weak. HF is stronger. Or we can look at these down here where we're looking at weak acids versus actually strong acids. So again, the trend goes increasing acidity as you go across. So you can kind of take a couple of points and compare those things that you kind of know, and then you can figure the trend out instead of trying to remember it. What about the oxyacids? So in the oxyacids, we have some element in the middle. It could be chlorine, bromine, carbon, sulfur, phosphorus, any of those guys. And there's an oxygen bonded to that element and a hydrogen bonded to the oxygen. All of the hydrogens in an oxyacid are bonded to oxygens, not directly to the central atom. So here we're looking at the strength of this bond. The polarity is correct. Oxygen is more electronegative. Hydrogen has the positive end of the polar bond. But the things that are bonded to this element can have an effect on the strength of that bond. So, I'm getting ahead of myself. That's on like the next slide. The electronegativity of Y effects. So if Y is very electronegative, it's going to pull electron density towards itself. Electrons like electronegative elements, and they just come and trying to crowd around. So that pulls electron density away from the hydrogen, making it easier for that to leave without any electrons. Does that make sense? So if we look at HOI, HOBr, HOCl, so this is hypochlorite, hypochlorous, hypobromous, hypoiodous acid. We see that HOI is the weakest, and HOCl is stronger than the other ones. A way I would remember this is I'd ask myself, well, what about HClO4? That's a strong acid. Do we see HBrO4 as a strong acid? No. So the trend must go the other way. Here's number of oxygen atoms. So the number of oxygen atoms that are bonded to that central atom Y affect the acidity as well. Because oxygen is electronegative. And so the more oxygens you have around that element Y, the more it pulls electron density away from this hydrogen, causing it to be a stronger acid. So here's the progression with number of oxygens: perchloric, chloric, chlorous, and hypochlorous acids. 4, 3, 2, 1. Well, we memorize that this is a strong acid. So they must be getting less acidic as we decrease the number of oxygens. And that's because these additional oxygens pull electron density away from the hydrogen and weaken that bond, make it easier for it to come off. Any questions? So let's test our knowledge. Which of the protons shown in red is more acidic? What we want to do is these are would both be oxyacids, right? Because there's oxygen, hydrogen bonded to oxygen. We want to look at the atom that the oxygen is bonded to. That's the same for both of these, carbon. What's different? The number of oxygen atoms bonded to this. Besides this one that's holding the hydrogen, we have one up here. And that's going to pull electron density away. There's nothing here. These are nonpolar bonds. There's nothing here to pull electron density away. This bond is going to be stronger. This bond is going to be weaker. The weaker this bond is, the easier it is for the hydrogen ion to come off, meaning it's a stronger acid. So this is more acidic. That make sense?